Okay, thanks everybody. Was that a little too loud? I'll stand back a little. And yes, thanks for hanging in. It's getting late in the day and I do appreciate your attention. So we're going to shift gears a little bit now and talk about NDT of ultra high performance concrete. And this is actually Daniel's work, and I am one of the folks on his committee. And Daniel is right now in the south of France. We're not sure whether or not he's drinking wine at this hour. And we have Megan is one of the PhD students. Raid's in the room as well. He's worked very hard on this project. Joel Harley, who's in electrical engineering and knows a lot more about the theory of this than the rest of us civil engineers. Kyle Writing, who might be over in the 236 meeting, or he may have just joined us, and myself. Okay, so again, a team effort. And what I want to do now is just take you through some of the NDT we're doing on ultra high performance concrete. So a quick outline of what we're going to do. We're going to go through our methodology, our experimental setup. I'm going to present you some field data and also some laboratory data. And like with most experimentation, the laboratory data always looks much better than the field data. So spoiler alert now. And we'll discuss some potential uses for our work. So obviously everyone knows the need for UHPC or the use for UHPC in our industry right now. And so what we're working on is a couple of aspects with regard to the fibers. Fiber alignment we're finding is a very important aspect, especially when we're going to get into lab testing of specimens. If we have the preferential alignment, which tends to be a big problem or maybe a big asset, depending upon how we want to look at that, we want to know, one, whether or not it actually exists, and two, if it does, is that something we can actually use to our benefit? There are obviously some benefits to aligned fibers in tensile specimens and tensile, structural components as well. And so this work focuses on quantification of fibers and also alignment of fibers within UHPC. The next question might be, well, can this work with FRC without UHPC? The answer is there are applications to that, but we have not gone down that road. And as we talk about materials that attenuate, that could be a potential issue. Okay. So with respect to this testing we've done so far, we're going to talk about computer tomography scanning as the most effective method for determining. But obviously this requires the use of cores. It's a destructive test. Not exactly what we want to do is create a structure made of UHPC, then go out and start making it Swiss cheese UHPC right after it goes into service. So that's pretty much a non-starter for our folks and our friends at the DOT. Non-portable and also slow. I got one little bullet in line here regarding ultrasonic methods not being reliable. We've done an exhaustive search and an exhaustive set of testing with some, I'll say what is P-wave NDT testing using ultrasonics. We've had a lot of luck using these P-wave sensors for everything else we've tried on concrete, including detection of flaws behind steel. However, when we got into using it for FRC or UHPC, the signals were scattering too much and we just were not able to get what we would hope for with respect to usable data. And so we switched over to magnetic methods, and this work is born after about 18 months of research on that path. Okay, so with respect to the theory, we're using an inductive sensor, or really what is a magnet, a ferromagnetic, and that produces a field which is picked up by the sensor, and the path length determines how much fibers we can sense at a time. So there's a inductance path, and we'll talk about that data as we move forward. The design itself is a pretty simple magnet, basically turning a bunch of wire, in this case 210 times, using an American wire with I believe it's 7.5 microhenries, and that's 25 gauge magnetic wire. And so we're building these magnets in-house. That's the nice part about it is one of the things Florida DOT wants to know is, can they have a relatively cost-effective solution without having to spend, we'll say a significant amount of money on NDT equipment. For those of us who know the NDT industry pretty well, there is no cheap toy to play with. We're usually spending, on the orders of tens of thousands of dollars for anything we purchase. So that's what we're excited about with this, is we can do this on fractions of that cost. Okay, and so very quick, our magnetic path length explanation. We have our electromagnet. Can you guys see the red? Okay, sweet, thank you. Our path length, which is, obviously dictated by the geometry of the magnet itself. We have fibers in there, and this is our UHPC specimen. And this is what it looks like a little bit closer. And we have our LCR meter, which basically measures our data as it comes in from our magnet and what we're getting with the UHPC. And so this is what the laboratory equipment looks like. This is generation 1 of the magnet. So let me go back real quick. And that's really our final generation of the magnet. You'll see there's much more turns. So before you ask, is that really the one you were using in the lab? Well, very first version of it is, but that's not what we're currently using. Okay. So what was part of our work here was really optimizing the magnet itself. And so part of this has some parameters regarding frequency, shape, size, and the number of electromagnets. Okay, I'm going to talk about frequency and shape at the same time. And part of this is because the efficiency of the shape also dictates how we measure it with dictates the frequency we measure. And what we've found out with this, and my apologies for the typo here, we've found out that basically using 1 kilohertz or 1,000 hertz for our signal was the best frequency for our UHPC, and this is basically because we need to stay below resonant frequency, and that's when we don't stay low enough in our frequency, we tend to get data that doesn't make sense or scatters when it's too high, and then when it's too low, we get data that's not very usable as we get distances that are further away from the magnet itself. And part of what we're doing here is we want to be able to detect fibers at depth or fibers at a distance away from our magnet. Okay, and then what we see is with 100 megahertz magnet, it didn't work at all. Now, that's part of it. And also the shape itself. We have the shape selection. The 2 primary magnets out in the industry or most widely used are the Pancake coil here and our U magnet, which we've seen several photos of so far. And so when we went ahead and did some inductance charges using both, we see that we got a lot more signal using our U-shaped magnet rather than the Pancake coil. So that pretty much dictated where we were going to go with our piece of equipment here that we're developing. And so from there, we went into size of magnets, and basically, like most things in the world, we see that the larger we have, the better off of the signal we get. So over here, we have a little bit of a larger cross-sectional area, and that's compared to a smaller cross-sectional area. And we just get more flux, we get more energy, and we can see more within the UHPC. Now, there's a number of electromagnets. And this I'm going to talk a little bit about. We have more than one, and they are aligned differently. But because we're in the patenting process, there's still some things I can't really talk about with what we're doing with this until I'm free to do so per the University of Florida. But basically, you need more than one magnet to detect alignment. And using that, and you can even use more than 2 magnets to detect alignment. So we have scans that are perpendicular to the direction and parallel to the direction of motion. And that gives us a relative idea of what our XY orientation is based on those ratio in 2 directions. And so if the ratio is greater than 1, the fibers are more aligned relative to the parallel direction and vice versa. Okay, and so here's our first iteration of a device. And if you say that looks kind of like a mop handle and some wheels and a mess of wires, that's pretty much what we thought too. So we decided to go ahead and clean it up for version 2 and 3D printed some stuff. And of course, in true Gator spirit, got our half orange and half blue. You know, we have our ride-along sensors. We're still working on a more compact design, and we know we can get that. But for our initial testing, this is given us very good performance, so we're quite happy with it. Okay. So calibrating the device itself, there were 2 aspects of what we were doing for calibrating. One is we're trying to detect fiber content, and this is not an easy task. So we basically wanted to calibrate using our lab specimens with 1 to 3% percentages. And then from there, we can decide whether or not we can go with height and depth measurements. In other words, once we know our fiber percentage measurements are any good, can we then go ahead and do more with that based on spacing of magnets, so on and so forth. And so I'm going to first talk about our wonderful lab data. And that's as good as the data is going to look for the rest of the presentation. So what we see is, as we started about 1%, we have one inductance around 100, and we get towards 3%. It's a little bit higher than a 1-to-1 ratio with inductance to inductance charge versus our fiber content. But it's, as we can see, a nice linear trend. And laboratory data tends to do that for us, right? So moving forward, we also then did decide, we took our 2% fiber specimen and went ahead and said, okay, if we space our magnet or get more distance between the magnet and our target specimen, what happens? And what we see is obviously a drop off in charge because we're getting less conductive material between the magnet. And this becomes important because one of the things we want to know is, can we detect fibers in a large scale UHPC element? Florida DOT is currently using, and I can show data if I have enough time at the end, I have a bonus slide, so to speak, of some of these large members, but we're talking about using astrogirders. We're talking about using octagonal piles, and can we get all the way through those? And the answer is with a lot more power, maybe, but as we're looking here, we're getting to about 5, I believe this is 5 inches, sorry, there's not a scale on that. And so then we went out into the field and we did some specimen preparation, which was basically large scale specimens DOT have in their structures yard. And we basically went up, marked them out, and took some NDT specimens, then took some cores out of those specimens, scanned those, and compared the results between the two. So when I start talking about field data, I'm talking about really giant laboratory specimens that are in the FDOT yard at the structures lab, and actually Steve's lab up there. And so again, using our ugly version 1 device, it really didn't matter which one because we did get the same effectiveness from both devices, version 1 and version 2. We basically just ran our device down the UHPC, in this case, the HB or the H pile, whatever you want to call it, and got data from there. And so again, I call this a field specimen. I know it was made at a DOT lab, but the process from the folks we spoke to at DOT, they basically said, yeah, this is what we expect to see in the field. Okay, and some of the things we see is you see some pretty interesting data when it comes to highs and lows. And so let's just take a second and digest this data. What's really going on here? So we run down our HB and we see we have a lot of inductance or a lot of fibers, and then it kind of drops off a little bit as we go down and up and down. And so basically what we're learning is a couple of things are happening when we place these piles. And one is we're getting differences in fiber alignment, and also we're getting a little bit of differences in fiber content, depending upon where we are. And basically that's, if I can think of putting the chute in here, putting the chute in here, and then all of those fibers kind of flow away and they align. Okay, we know this is happening, and we're really just starting to scratch the surface on what this really means with respect to structural implications. There's a lot there, but I'll go ahead and save that for maybe after the talk. So then we went ahead and took some cores out of the piles, and we have certain areas in our H piles and other piles as well that we took cores from. Went ahead and did some CT scanning of the H pile for fiber analysis. And so this one was scanned, and really, imagine the I-beam being turned on its side, oriented as shown for the Z-axis perpendicular for the quartz surface. So you can kind of see a nice indication of our core, and that gives us a lengthwise to the H pile itself. Okay, and so the fiber orientation analysis with the CT scanner, basically it was analyzed in 3 directions, X, Y, and Z. And so blue gives us aligned with the axis, the red gives us fibers are kind of perpendicular, and green gives us something in between, right? So can we get alignment, preferential alignment, or do we have what we would consider to be more of a non-aligned or random alignment? Okay, so we made markings on each core before taking it out. This is really critical. We wanted to make sure that whatever we were doing in the field went back and was translated to the CT scanner with a good degree of reliability, we'll call it. Okay, and so we marked those out pretty good, made sure the aluminum strip held in place, and then we went ahead and threw those in the CT scanner. And this might be the most beautiful slide I have to offer you, or ugly, depending upon how you want to look at it, but I think this is awesome work. And this really is a tribute to Megan and Raid, who are here in the room, and their work. But what we found out is as we started doing the CT scanning, we see that there are potentials for orientation preference. Okay, so some of these that we see that there are distinct layers of concrete that have preferentially oriented fibers. You can kind of see here and here. And then we have other areas where there's not as much orientation. So we are seeing that when we make our large specimens, there is fiber orientation. And I don't think that's non-starter with respect to UHPC, but it is something we obviously have to be aware of. So what does that really mean when we start looking at fiber percentage and our using our, we'll say, newly developed, somewhat proprietary device here with a bunch of magnets on it? Well, this is the bad news. And what I mean by that is we have our, our NDT data using our magnet, and we have our CT data, and we see that, well, it's not the greatest agreement when we get into fiber percentages at around, between the 1.5% and 2%. So am I ready to call this a device ready for QC of UHPC? Not yet. But let's look at the good news. If we want to use this for potential orientation, we see that, well, using the methodology developed by Daniel and our team, we can get a good idea of whether or not we are seeing preferential alignment. And so that does give us a good amount of data as to what we expect from our placement of our UHPC as it goes into the beam specimen. And so some really simple conclusions. Again, this is research in progress, and we are excited about the direction in which this is going, but we do feel promise in our NDT methods that have been developed here. We feel very excited about when we create stuff in the laboratory and validate it very simply, right? And then when we take that out in the field, we're a little less excited about that. And we are pretty excited about the fact that we've done pretty well with orientation of fibers. And so this gives us some promising results for further development of what we're implementing. So that's everything I have, Steve.
Thank you, Dr. Ferraro. Any questions in the room?
You said that you were able to get pretty good results on the orientation of the fibers, but in the previous slide with the cylinders, you could kind of see that there were several different orientations along the depth of that web or along the thickness of the web. How precise is, so I'm looking at the y-axis here, kind of there's several bands of color that are shown. How precise are you when you're kind of running this piece of equipment along the web?
Precise meaning
like your lateral
location?
Yeah. Like how much are you picking up laterally between the difference here on the CT scan? When because you said you ran it along the web of the H pile, you run it like several times?
Oh yeah, no, we're going for repeatability. This is not like one scan and we took our best data. This is, when we're going into our NDT data, we're having averages of scans. And so we'll rerun those over and over again. And so
I guess like left to right here, were there several scans along this?
No, this is
the web.
Oh, I see what you're saying. So this is our CT analysis, not our NDT analysis. Correct. So this is just a single core that you're seeing actually a CT image of the fibers themselves.
Okay.
When we run through and go down well, let's kind of look at it this way, I guess. Where is this slide?
So your device is kind of smearing the CT data in that y-axis plot.
Let me think about it. I want to make sure that I feel good about what you just said.
Or is it getting the surface more than it is?
Yeah, I think it's getting the surface. I'd say that's fair. I mean, we haven't really gotten into, more parametric aspects of geometry with fibers, and I think there's more to be done there. Okay. So in the end, is it a smeared average of everything? Sure, that's an appropriate way to describe it. Yeah. But yeah, I think I'll leave it there. But that's a good point. I like that.
I think that's all we got time for. So thank you very much. Round of applause.